Hi everyone, in this clip I want to talk about conservation laws, and in particular we'll focus on conservation of energy. Some quantities in physics are important because they are conserved. They are quantities that are often abstract, but they are also very special. It's often hard to have a feel for these quantities because they do not really correspond to something that is meaningful in the real life or that is concrete. However, we can use these quantities to take very different approach to solving problems. Because when a quantity is conserved, it means that a quantity does not change as time passes. So the value of the quantity at time 1 is the same as the value of the quantity at time 2. That can be very powerful. You're actually already familiar with some of conservation laws. You probably already know about the conservation of mass in chemical reaction, maybe conservation of charge, when we have radioactive decay as well. In this class, we will focus on 3 conservation laws. The first one, I'm sure you're familiar with already, conservation of energy. And then we'll look at 2 others that are linked to momentum, conservation of momentum and conservation of angular momentum. These 3 methods can be used to replace the use of Newton's second law, either with diversion with force or with torque, so that we can approach problem differently, and sometimes actually they are better than Newton's laws. They are applicable in cases where the Newton laws will fail. So we will start today by looking at conservation of energy. For isolated system, that is a system that is left alone, mechanical energy is conserved. This means that the energy at time 1 is the same as the energy at time 2. However, in some system, there will be work that is done on the system. We can still account for the change in energy in this system because we know that the work energy theorem tells us that the net work done on the system, so the work done by all the forces combined, will correspond to the change in kinetic energy. So by using this, if we are able to calculate the work done, we can still use energy to solve problems, even though the energy of the system is not really conserved. There's a change, but we can know by how much this energy is changing. So we will try to combine these 2 equations together to get it into a form that we can use to solve problems. The first step to get there is to distinguish between conservative forces and non-conservative forces. Some forces are special because they conserve energy. These will be obviously the conservative forces. So what's special about these is that the work done by these forces when going from point A to point B is the same for all paths. Okay. The 2 examples that we'll use of conservative forces are gravity and the force due to springs. Let me give you an example. So if you have a ball that is at the bottom on point A, and we want to get it, let's say, on a table that is at point B. If you want to calculate the work done by gravity, either using the orange path, that is a very weird path that is going all across, or on a straighter path that is going along the green line, or maybe going horizontally first and then vertically. In all cases, the work done by gravity will turn out to have the same numerical value. So we say that because of that, the work done by gravity is conservative. The force due to gravity is conservative. So for these forces, we can actually make our equation that we had previously a little bit easier, because the work from conservative forces can be written as a change in potential energy. So that is the potential energy at the end minus the potential energy at the beginning. So here point B and point A. And don't forget the extra negative sign in front, because the work done is the negative of the change of potential energy. Using this, we can separate the net work done on the system into the work done by non-conservative forces and the work done by conservative forces. So the work done by conservative forces I can replace by the negative of the change in potential energy. Now if I bring this term on the right-hand side of the equation, I just obtained that the work done by non-conservative force is equal to the change in kinetic energy plus the change in potential energy. Or if we want to explicitly write this, that would be the final kinetic energy minus initial kinetic energy, and same thing for the potential energies. Another way to rewrite this equation is to bring all the term that corresponds to the initial time on one side and keep all the term for the final state on the other side. So we end up with an equation that looks like this. Kinetic energy at the beginning plus potential energy at the beginning plus the work done by non-conservative forces is equal to the final kinetic energy plus the final potential energy. As I said before, in this course we will focus on two different types of potential energy. Let's look at them in more detail. So the first one is the gravitational potential energy. To calculate it, it's actually pretty straightforward. You have to take the mass of the object multiplied by the acceleration due to gravity, usually 9.8 meters per second square if you're on Earth, and then multiply by the height of the object. Okay, I'll come back onto how we define this height in a couple of slides. The other potential energy that we'll be dealing with is the one for the spring. Potential energy of the spring depends on two values or two quantities. There will be the spring constant that defines the stiffness of the spring. So is it a spring that is easy or hard to stretch or compress? And then the delta S corresponds to either the elongation or the compression of the spring. So you see that whether we compress or stretch the spring, the potential energy that we will obtain for the spring will be positive in both cases. Let's now take a look at the non-conservative force that we'll use in this class. So there are mainly two contributions. The first one is friction, and when we want to calculate the contribution from friction, what we'll want to do is just to calculate the work done by friction. So force of friction, scalar product with the displacement, or if you prefer, the version that is using the angle between the two vectors. And the other quantity is usually coming from the applied force. This will include tension, push, pull, all of these external force that we apply on the system. And to calculate the energy, or the transfer energy, the work that is done by these, we'll do the same thing, F applied, scalar product with the displacement. So we are now ready to put all of this together. So to summarize, we have a big equation that we want to go back to for conservation of energy. It includes the mechanical energy of the system at the beginning, the mechanical energy of the system at the end, and the transfer of energy to or from the system that is done by the non-conservative forces. Kinetic energy is given by 1/2 times the mass times the speed squared. The potential energy, actually, there are two contributions to these terms. For us, the potential energy due to gravity, mgh, and the potential energy due to the spring, ul or us, which is equal to 1/2 k delta s squared. For the work done by non-conservative forces, in general, there will be two contributions, one from friction and the other one from the work done by force applied. Right? So the goal when you'll try to use conservation of energy will be to start from the big equation here and make sure that you include all the contribution to the energy that there are in the problem. So if there's a spring, make sure that you include the energy, the potential energy due to the spring. If there's a change in height, make sure you include the potential energy due to gravity. And if there's friction, you'll have friction. Make sure that you don't double do it. You see that the work done by gravity is not part of this in here because we already accounted for gravity by using the potential energy. To wrap it up, I would just like to explore a little bit more the potential energy due to gravity. Okay, the equation in here states that the higher the object is, the bigger h is, the more potential energy there will be. Okay, but this h, it's not necessarily clear how it's defined. Where do we take h to be equal to 0? Okay, actually it doesn't matter because what matters is the change in the potential energy. So in the end, it will really be the change in height that will be important. This is neat because it means that we can choose the 0 of height wherever we want. You just have to make sure that you make your choice at the beginning of the problem and you stick to it for the full problem. So for instance, just to show you an example, if we were to find the change in height and the change in potential energy with the height of the reference that is on the ground, when we take the ball and lift it to the table, well, at the beginning the height would be 0, and at the end the height would be the height of the table, capital H. So the change in height would just be equal to capital H, okay, HB minus HA. But if I instead wanted to take my height to be 0 at the top, then when I'm lower, the height would be smaller, so I would be at the bottom at minus capital H. And the initial height would just be minus capital H, and the final height would just be 0. All right, it's moving up. So when we do the calculations for the subtraction, we'll have 0 minus h, so that we'll get plus h. So you see the difference in height is the same. So the important thing to remember is make a choice for your height to be 0, a choice that simplifies your life, and then just stick to it for the rest of the problem. All right, we'll restart from there in class.